Hello students, thanks for joining me as we look at some applications of differential equations. The section title might not make a lot of sense to you right now, the specifics of it, but it will by the end of this video. So stick with me. Let's delve into why would we ever want to learn about differential equations. I think this question has already come up and I haven't really answered it yet. It turns out that many quantities in this world around us really follow a simple rule. The rate of change of the quantity is proportional to the amount of the quantity present at any particular time. Okay, that's a lot to take in terms of the wording, but really we want to kind of compare this idea of something being proportional to something being constant. And there are some things that grow at a constant rate, for sure, but that's not how most things in life work. So just to throw a couple examples out there that we're going to delve into, population growth would be something to look at. Interest, amount of money that you're making on the money that you've invested. It's not like you get the same amount every time. As you have more money in the bank, then you're going to get more money in interest. Same interest rate, but the amount that you're getting is proportional to the amount that you have in there. So we're actually going to look at a differential equation that says that in words. Okay, so back to here, and I want us to agree that this is what I just had on my other screen a second ago. I'll bring it back in simplified form. We had y equals k times x. Okay, and I know I'm switching out variables, but let me remind you how I started this video. The rate of change of some quantity, well, how do we express rate of change in calculus? There it is directly proportional to the amount of that quantity present at any particular time, and that would be my y. Rate of change of y with respect to time is directly proportional to the amount of y, whatever y is. So hopefully you can agree with me that that is a situation of direct variation. Now, let's go into calculus mode and let's just see what happens if I solve this equation. I'm going to solve for y, and I want to figure out what kind of an equation actually ends up with this direct variation relationship when we talk about the rate of change. So maybe you already see it, maybe you don't. I'm going to have to do a little bit of work here to get to the point of seeing it, but I can do this. This is definitely a situation that falls right in line with what we've been practicing. Separate our variables and integrate both sides. So I'm going to start by multiplying by dt on both sides and end up with my lovely dy equals k times dt, and I'm noticing that I have a y on the right side, and that needs to go with my y on the left side. So I'm simultaneously going to divide by y to get rid of it there, and divide by y there. So I'm left with dy over y on the left, but I like to write that as 1 over y times dy equals k times dt. K, remember, is just a constant. Okay, so I technically could put that on either side. I like to keep it on the right because I don't like to look at just a dt anyways. And now I'm ready to integrate both sides. So let's integrate both sides and let's see what happens. So I'm going to start on the right side because that seems simpler to me. And on the right hand side, I'm going to end up with constant times my x variable, which in this case is time, plus my c and my constant of integration. And then on the left hand side, hopefully you're getting a little more comfortable with this. 1 over y is sort of my weird case. I've got to reverse my derivative rules. Integral of 1 over y, antiderivative is natural log of y. And I'm going to go ahead and put that y in absolute value bars there. So from here, I need to go ahead and solve for y. I'm just going to keep it in terms of that constant of integration. Keep it c right now because I'm looking for a general solution. So I'm going to convert this to exponential form is what I have to do at this point. So I'm thinking that there's a little e down here, base of my log, and e to this power is equal to the inside there. However you like to think about that. So I'm getting e to the kt plus c, that's all in my exponent there, is equal to y. Probably looks better if I write it like that. And I did have an absolute value bars here. At this point, I'm going to drop the absolute value bars because I'm recognizing that an exponential function is always positive. Okay, graphically, I'm always going to get a positive value. You can go e to a negative power, just converts it to 1 over e to a power, which is a really small number, but it's still going to be positive values. So I'm going to go ahead and intentionally drop the absolute value bars because I don't need them. We've practiced this a few times, but good reminder. What do I do with that c? It's not that it's wrong right here, but we would rather not have that in the exponent. So I'm going to use some algebraic properties here and rewrite that as e to the kt times e to the c. Separating when I have the multiplication of two terms with the same base, I can add the powers and get me to here. Okay, we're undoing that algebraic property of simplifying and separating it. Why? Because this is really just some constant of integration, so that's like a second c, a different c, but it doesn't matter because I don't know what that constant is anyways. So I'm going to go ahead and rewrite that as some constant times e to the kt. So I'm getting to the point that I have this solution to my differential equation, and my solution is y equals c e to the kt. We started with this direct variation equation and we just solved it. General solution is y equals c e to the kt. That should look very familiar to you. That is our basic form of an exponential growth equation, and you've studied these before, just not with the calculus part. You haven't been looking at the derivative of it, but you've looked at that. And think about what happens when you have exponential growth. A basic example is if you're doubling something. If you have a base of 2, then every minute, if something's doubling every minute, depending on what your time variable is, the amount that you have is doubling. So it's not a constant increase. The increase is proportional to the amount you have. The more you have, the greater increase you have, because doubling something bigger gives you a greater growth. So that's really, that gets us to applications in finance, medicine, biology, economics, all kinds of things. So this is a huge area of application when we talk about how is calculus used, how is this particular unit used. We're going to go through a couple examples where you can see this play out. I'm going to give you one other way of writing this before we move on, just as a way of generalizing. This is often expressed as y equals y naught times e, or y sub 0, whatever you want to call that, e to the kt, where that y naught is the initial amount and k is the growth constant. Okay, so if we want to, c is our constant of integration, but that is going to take on the initial amount, and we'll see that as we work through some problems. We're going to take a quick trip back to algebra. So just join me for a second as we look at something that you learned in algebra but might be a little bit removed from you at the current point in time. So we had something called direct variation and inverse variation. Okay, literally Algebra 1 class. Direct variation is an equation of the form y equals k times x, k being a constant. We would say x and y are directly variated, or are in a relationship of direct variation when y equals k times x. If you solve that a different way, rearrange it, you could divide by x and you get y over x equals some constant. Direct variation, as just look at that equation for a second and agree with me that as y increases, x will increase in order to be equal to some constant here. So y and x are going to have to increase proportionally, if I can use that word. And we could even just think about a simple fraction there. If we had 2 over 3, y is 2, and x is 3, just to put some numbers in there, then if y doubles, if y increases to 4, then 3 is going to have to not increase by 2, but increase by a factor of 2 to 6 in order to be equal to, again, the same constant here. Okay? As we look at a graph, that would be as x increases, y increases, sort of a positive correlation. Inverse variation, just for contrast of how is this different than something else. Inverse variation, going over to my other type, would be an equation of the form y equals k times 1 over x. That makes sense in terms of what we think of when we think of inverse reciprocal. But really I like to think of it as the inverse part is as y increases, x is going to decrease, or vice versa. If I multiply on both sides by x, I get down to the product of x times y is equal to some constant instead of the quotient. So if x times y is going to equal something and I want it to equal that same constant, then as x increases, y is going to have to decrease in order for them to multiply together to give me the same number. Okay. We're going to be living over here in direct variation, but I needed you to remember sort of the distinction there. And we're really going to focus on this equation here. When I divide, well, really these two. So two different ways of expressing the same things. If you want to jot those down so you can refer back to them, I'm about to go to a different screen. But we're about to put the calculus in, because the calculus is going to give me a way of expressing this direct variation, directly proportional relationship when I'm talking about a rate of change. So instead of y and x, I'm going to have a dy dx and another variable representing my amount, y or a or whatever I want to use. Y equals k times x, I'm right here. This became a rate, and this became my y, or my... Okay, so a specific example where we see this. Instead of interest being added at discrete intervals, a lot of times interest is added continuously at a rate proportional to the amount of money. So I'm going to pick up on that phrase there, and I'm going to try to figure out how I can write a calculus statement that describes exactly that. Added continuously. So the rate is proportional. I'm going to start with the rate. That's the rate of interest being added, or the rate of change of the amount of money that I have. I'm going to use A to represent the amount of money. dA dt, my rate, is proportional. That means that equals the amount of money times k, or in this case, I think it's going to make more sense to call that r. So I'm using r to represent some constant that I have, because in this case I'm talking about money. So just a quick flashback to what we had a second. Okay, hopefully that makes sense how I got that from the equation. Now I'm back in calculus mode. What am I going to do? I'm going to solve the differential equation. So if I'm solving the differential equation, well, I guess I have to rewrite it first, so let's rewrite it. And let's put my a on the left, so 1 over a dA equals r dt. And then let's integrate both sides. Going a little quicker this time, so I'm going to get natural log of absolute value of a is equal to RT plus my C. Okay, remember T is just my variable this time. So solving that, I have that base of E for my exponential, so I'm converting from log to exponential equation. So I'm going to get e to the RT plus C is equal to my amount. It's acting like my y. I'm going to rewrite that as e to the RT times e to the C, which is going to become CE to the RT. That's just some constant. Okay, same process I just went through. Let's put that together. So I ended up with this. A is equal to, rewrote the right side a few times, this. So A equals CE to the RT. Supposing I took that constant of integration, unknown C, and changed that to a P because it's just some unknown. PE to the RT. Now that should be looking familiar to you. Good old PERT. Isn't that my equation that I have? For continuously compounded interest, PE to the RT. My initial amount is my P, my principal, and then E to the rate times time. That's what's happening when you have continuously compounded interest, is you have that interest is being figured off of the amount that you have, and it's the rate of change of money is directly proportional to the amount of money you have at any point in time. So kind of weird, we're coming in the back door, and we're approaching this from looking at the rate of change and starting with that. But what's really interesting is they all come down to the same basic differential equation that is a direct variation equation. Okay, we could, of course, do something with this like you guys did in pre-calculus and probably Algebra 2, and we could solve for the amount of money with the given situation. I'm just kind of showing you where these formulas come from, and we will get to I'm going to go ahead and pause the video and start a new video, just so this one doesn't become too long, and we'll get to what if I have extra information, then I can actually write a particular solution instead of just the general solution.